So if we don't know the population standard deviation, when we have a sample, we will still know our sample standard deviation. Okay? But if we don't know the population standard deviation, we can't use the standard normal distribution. We have to use the student's t-distribution, right? And remember there, the shape was influenced by the degrees of freedom. And the degrees of freedom was n minus 1. Okay? And in the student's t-distribution, we marked our position around our assumed mu naught, not with z values, but t values. So since we can't use z's, we can't do a z-test. So we want to do something called a t-test. But in this case, right, we still need our sample size to be large enough for it to apply. And the population, or if the sample size is small, we still need the population to be normally distributed. All right, so the example we're going to look at a sample of 360 one-year-old baby boys. They had a mean weight of 25.5 pounds, right? Remember that's X bar in this case because we're looking at our sample. And our sample standard deviation is going to be 5.3 pounds. That's going to be our S. A pediatrician claims that the mean weight of one-year-old boys is greater. That's going to be our keyword for our alternative high test. Greater than 25 pounds, right? Does the data produce convincing evidence at the alpha of 0.01 level? So first, let's look at our hypotheses. Right. The null hypothesis is going to be the value in our claim. So that's going to be that the true mean weight is 25 pounds, right? That's the numerical value in our claim. The alternative hypothesis, right? We're going to look for our keywords, less than, greater than, more than, fewer than. In this case, it's greater. So we're going to assume that the true value is going to be greater than our null hypothesis value. So our alternative hypothesis is that the true mean is greater than 25. The greater than, right? Greater than means we're looking to the right, so we're looking for a right-tailed test. And since we don't know our population standard deviation, we're going to have to use a t-test, which is going to be based on the student's t-distribution. So to do a t-test on a TI-84 calculator, we'll go to Stat, Tests, and t-test. And this will do the calculations for us. And the values we put in, right? We're going to input the statistics because we have our claim, we have our sample mean, sample standard deviation, etc. Mu naught, that is our null hypothesis claim again. X bar is our sample mean. Sx is our sample standard deviation. N is our sample size. Remember, we had 380 baby boys. And the alternative hypothesis is the greater than, right? So you'd go over to the greater than and select that to get our right-tailed test. We hit calculate, it's going to output a bunch of things, and again, the thing we're looking for is P, right? So in this case, it's 0.03715, and we're going to compare that to our level of significance. All right, for our level of significance of 0.01, we see that 0.037 is greater than alpha. So we're going to fail to reject the null hypothesis. The data is not strong enough to support the fact that it's greater than. So this mu naught, our null hypothesis, is still going to be reasonable. And so the thing we say is that there is not sufficient evidence to conclude that the weight of one-year-old boys is more than 25 pounds. We don't have a strong enough data set to do that. The data is not significant at the 0.01 level. Now notice that if we had done the 0.05 level, then our p would actually be less than alpha, in which case this data would be sufficient, right? This data would be significant. There is sufficient evidence to conclude that the 1-year-old boys weigh more than 25 pounds. So sometimes our choice of alpha can change our conclusions. So be aware of that.